And we are back. All right, today we're going to talk about resonance, where you can have more than one correct Lewis structure for a molecule. So an example of that is NO3-, or another one that we've dealt with in the past, which has the same number of valence electrons, is CO3 2-. So with NO3-, the first time you draw the Lewis structure, you might draw the double bond down here between the nitrogen and the oxygen below it. However, there's no reason why the double bond couldn't be up here towards the oxygen on the left or towards the oxygen on the right. So with resonance, what you do is there is more than one valid Lewis structure. So since they're both polyatomic ions, you put it in brackets with its charge. But between those resonance structures, you put a double-headed arrow. And you put all the different possible Lewis structures. So one with the double bond towards the left, one with the double bond towards the right. And what occurs, since there's 3 valid Lewis structures, what happens, the actual structure is just an average of these 3 resonance structures. Because when you measure the bond length of each of these NO bonds, they're actually all the same. Because each of these spends 1/3 of the time as a double bond and 2/3 of the time as a single bond. So each of these are considered almost as a 1 1/3 bond, since 2/3 of the time they're a single bond and 1/3 of the time they're a double bond. So all of these bonds are equivalent. Okay, the only thing that's different here is just the placement of electrons, meaning here the electrons are delocalized. Last week we talked about the localized electron model, in which those electrons stay on one atom. Now here they're delocalized, they're moving around the entire molecule. So a couple of other examples of resonance, like we said, CO3 2-, or we've already talked about SO2 or ozone, O3. Those structures are similar. So in SO2, we have the central sulfur. On one side, there was a double bond. On the other side, it was coordinate covalent bond to the other oxygen, with the lone pair on the sulfur here. So there's no reason why the double bond can be on the right and the single bond on the left. So this can have another resonance structure with the double bond on the right and the single coordinate covalent bond on the left. Okay, and the same thing for ozone. All right, that's all for today. See you next time.